Jay, we will start the session now because after showing the video, like it will take time.
The video is getting downloaded. Maybe take a couple of seconds.
Okay.
కెమెరా ఆన్ లో ఉంది.
So Sonal, you want me to share my screen and play that video? Sonal, you want me to play? I mean, stop your screen sharing and start playing the video?
No, Jay. Now Mandeep is able to share. She will be sharing.
Oh,
Yeah.
chalo, badhiya.
Make me the co-host. I'll share.
Yeah, you are already co-host, Mandeep. So, good afternoon, everyone. Welcome to the 8th session of Sparkle series, and this is the second last session. So, I hope you all are excited for this session, and I hope you all have learned so many things from this entire series, right? So, in the last session, we learned about, we learned so many new concepts like arithmetic progression, using the calendars, the calculation for modulo, creation of different shapes by marking the points in circle. In this session, we are going to learn something very interesting related to electricity, magnetism, and electromagnetism. And I know this is a very important part of the syllabus, so we request you all to remain focused in this entire session and enjoy the session. So before we proceed further, let's see our
అర్షిత
web
ఈరోజు సోనాల్
we
శుభం అంట.
we request all the
सोनाल
participants
शुभम.
to be on mute.
अरे इससे साउंड क्यों नहीं आ रही सर? इसमें
लास्ट वीक కూడా ना
साउंड नहीं आ रही, फोन में आ रही है.
Yeah. So Mandeep, can we see our web page? So this is our Sparkle web page where we get all the information related to our Sparkle series. So we have the joining links, the material list, the assignments, everything on this web page. So I request you all to go through this and do the assignments. The assignment link will be visible in some time. So this is the Sparkle series, and now since we are moving forward, and this is the second last session of Sparkle series, we want to show a testimonial of the students from JNV Indore, who like they have shared their entire experience of Sparkle series. So I request everyone to see it and also request you all to share such testimonials with us. We want to know how much you have learned from this entire series and have you enjoyed this. We want to know your feedback. So request everyone to see the video. Mandeep, you can play it.
This lovely congregation of Vigyajyoti. It's really an opportune moment that Jawahar Navodaya Vidyalaya Indore got to be the part of Vigyajyoti scheme and Sparkle series. This platform gave us the opportunity to showcase our inquisitiveness in field of science. Sincerest of our gratitudes to Samiti and the government for this initiative of Vigyajyoti. We also highly acknowledge the efforts of IIT Gandhinagar and their ever-inspiring professors who acquainted us with the percolation of various fields of science.
शुभ संध्या सभी को। मैं पलक द्विवेदी कक्षा 11वीं एवं जवाहर नवोदय विद्यालय मानपुर इंदौर की छात्रा आज आप सभी के समक्ष अपने अभी तक के विज्ञान ज्योति सत्र के अनुभव लेकर उपस्थित हूँ। जैसा कि हमने हमारे पहले सत्र जो कि कागज के खेल पर आयोजित था उसमें सीखा कागज को बिना व्यर्थ किए एरिया को पेरीमीटर में बदलना, A4 साइज के कागज से सबसे बड़ा इक्विलेटरल ट्रायंगल बनाना, A0 से लेकर A4 तक के कागज की चर्चा शामिल थी। वहीं हमारा दूसरा सत्र जो कि साइंस ऑफ साउंड पर आधारित था उसमें हमने वाइब्रेशंस और वेव्स के बारे में जाना। हमारा थर्ड सेशन जो कि ट्रिग्नोमेट्री पर था उसमें हमें कई नई चीज़ें जानने को मिली। सत्र चौथा जो कि कंप्यूटेशनल थिंकिंग पे था उसमें हमने बाइनरी डिजिट्स के बहुत सारे इस्तेमालों को जाना। वहीं हमारा एक सत्र लॉज ऑफ मोशन जहां हमें न्यूटन्स लॉ ऑफ एप्लीकेशंस की बहुत सारी चीज़ें पता चली। हमारे समस्त सत्र हमारे लिए बहुत ही ज्ञानवर्धक रहे। हमने इन सत्रों की मदद से बहुत सी जानकारियाँ अर्जित की जो कि हमारे लिए मददगार साबित हुई।
As my friend Palak told you, the first session was about the Kagas Ke Khel adventures of A4 where we learned about the menstruation. The second session was about the science of sound where we learned about the vibration, waves and made many types of toys inspired by it. We enjoyed the activities and had a lot of fun exploring the theories behind sound. Activities presented by the students of our Vidyalaya also received appreciation from respected DC sir and the rest of the team. Next to that was a session of trigonometry. इस सेशन में हमने अलग-अलग तरह की सब्जियों से विभिन्न प्रकार की आकृतियां बनाना सीखा। ककड़ी, लौकी व आलू से साइन वेव, पंचकोण, षटकोण व अष्टकोण बनाना सीखा। व अनोखे तालों की ऐसी चाबियां बनाना सीखा जिनमें एक साथ 3 आकृतियों को देख सकते हैं। नवोदय विद्यालय समिति ने हमें यह Then we jumped to the session of computational thinking, in which we learned the basic and splendid use of binary digits. We used them for sorting cards. We used it to make cards consisting of stories of Ramayana and arranging them in the chronological order of events with the help of binary code. We were very amazed to do so. It was one of the most coveted activities. And here comes the chance of the session of laws of motion, the one we loved the most. It was really fun going through the concepts of Newton's laws of motion, which we learned in class 9, and exploring the vectors which we left untouched. Performing activities of this session was immense fun. We worked on all of the 3 laws of motion. We did activities of dropping the basketball, activities based on inertia of rest and motion, and much more. This brings me to the end of my experience. This is Pridhima Kaushal, student of class 11, JV Manpur Indore, signing off for now. Thank you and have a pleasant day.
Thank you for sharing this with us, Mandeep. And I hope you all have seen the video and see that how conceptually it was clear to these students and how nicely they have summarized the entire Sparkle series. So congratulations to the students of JNV Indore. And we request everyone, you can also share your experience with us. As I always say, do share, keep sharing your projects with us and keep learning. So now handing over to Ashutosh. Ashutosh will be taking today's session.
Hello, am I audible?
Yes, Ashutosh, you are audible.
Yes. Good afternoon to everybody. Welcome to this penultimate session of Sparkle series. We are so happy to be with you, and this has really been a great journey for us. This would be my final presentation, so I would like to say that it has been so inspiring for us as well, that when so many students across India, so many teachers tuning in, and all the videos and photographs that you sent to us of the activities that you tried, it is so inspiring for us, and it propels us to keep exploring and learning ourselves. And we hope that this does enliven maths and science for you in new ways, more than concepts, if it brings back the joy in your eyes about learning, and if it gives you a new perspective to see things around us in a different way, as well as gives you the perspective that experiencing things ourselves, experiencing and stimulating our senses is extremely important. Rather than just pen and paper, it is very important to have a very physical embodied understanding of these things. And our attempt is to do these experiments primarily because when we do the experiments, not only do we have joy, but there are so many complexities that nature throws to us when we do something. So we might understand the theory of something, but when we actually do it, we realize that despite knowing theory, the activity doesn't work. So then we have to troubleshoot. It throws up a lot of craftsmanship challenges, and there is perseverance that is involved to troubleshoot the things, to make it work. So it's not just the concepts that are important, and it's not only for the concepts that we do the activities, but also to learn these engineering skills, these important collaboration skills, because we have to do these activities with each other. So thank you so much for trying all these things, sending us your feedback, your activities. And today we have another very interesting session, and I'll take you to my slides. Sonal, this is visible, right? The slides are visible.
Yes, Ashutosh, it is visible.
Yeah, so as we say every time, this is our goal, this is our purpose for the lab, that can we bring back the gleam in the eyes of everybody, not just children, but adults. This is our beautiful lab at CCL IIT Gandhinagar. This is the auditorium where we have our visitors and teachers workshops. And today's very interesting session is on electricity and magnetism. And we will take a journey from Thales to Faraday. There's a lot to be covered under electricity magnetism, and there is a certain portion that we will focus on, which is as is visible over here, Thales to Faraday. A lot of things happened after Faraday as well, but we believe that these experiments that they did in the 17th century, 16th century, and even in 5th, 6th century BC, they were so fundamental, simple, that they enable us to get a very rudimentary approach to science, as well as a very fundamental approach to how those people designed those experiments. So these are some of the figures that you see on your screen of 4 gentlemen. There are hundreds of others who contributed, but we'll focus primarily on these people. So what we will explore is, we'll try to hopefully explore all these 7 things. We'll start with static electricity. We'll see a very beautiful and fascinating toy that was made by a high school girl about 17, 18 years ago, which employs the concept of static magnetic levitation. We will find out about William Gilbert's discoveries. We'll explore how a frog, ek jo medhak hai, it is, we should thank a frog every time we see a frog for all the electricity and batteries that we see around us. So we'll see Galvani's frog, the Volta and his first battery. We'll see Ørsted and how electricity and magnetism came to be woven together, and how this was the beginning. His discovery was the beginning of integrating these 2 seemingly separate domains of electricity and magnetism. We will explore the work of Faraday, his motor and generator, and we'll explore Lenz's law with some activities. So now, so now all of you must have, when you read about static electricity, and I would like to hear feedback, have you heard of the word amber? We use the word amber so many times, right? You must have read in your textbooks, your teachers must have told, ki, in static electricity, they use something called amber. Does anybody know what amber is? Can anybody share what is amber, if you have heard of it? Sonal, you'll have to manage the participants for me. Anybody can unmute and like just share what is amber. What do you think amber is? Is it a girl's name? Like in the West, they have amber as a girl's name, right? So was she a scientist, ancient scientist who did static electricity experiments that we hear so much about? What is amber? Anybody? Any guesses? You don't have to be right. Like, I think it should be clear by now that we don't focus on being right or wrong, but you can make an attempt. Should we go ahead? Nobody wants to participate?
You can answer in the chat box also.
Okay, 10 more seconds if anybody wants to share anything. It is interesting to know, for us to know, what do you think is amber is? Firstly, have you heard of it? Like, if you have heard of it, please raise your hand so that at least we can visually see. All the girl students, if you have heard of amber word used in static electricity, please raise your hand. You haven't heard it in your textbooks, in your classes? Are people raising their hands?
They are writing tree resin, hard resinous part of a tree, type of road.
Okay.
Tree resin.
Okay. So firstly, at least raise your hand if you've heard of amber in any textbook, outside textbook, anywhere in terms of static electricity. Anybody who has heard? Okay, let me ask the other question. If you have not heard of amber, please raise your hand. If you have not heard about amber before, please raise your hand. Tall. You're not raising your hand. Okay, I can see some. JNV Champawat is sharing. JNV Katni, you're not raising your hand in either of the questions. Others cameras are off. Like if you can switch on your cameras, it will be great. Okay, anyway, so we'll move ahead. So some people rightly mentioned that what amber is actually it's a so from trees sometimes a sap comes out, and if that sap gets solidified and over millions of years, if it gets fossilized, so you must have often heard about fossils that we see of prehistoric animals or plants. Similarly, it's like a rock. So it's a solid rock-like thing, but it's not inorganic material. You can call it an organic material. It comes from trees. And how does it look? I'll quickly show you. I thought this was important. So on the left, you can see this golden color. Often it also has different colors depending on the type of sap there is. So, and this is a very interesting photo on your left. You can see an ant inside it. So many millions of years ago, there must be an ant walking on a tree, and some sap from the tree came out, it got trapped in it, and it got fossilized along with the amber. So this solid yellow golden type thing is called amber. And if you've seen the movie Jurassic Park, there's this famous scene in Jurassic Park, and this person has made a Jurassic Park to revive dinosaurs. And he carries a stick with himself, and on top of that, there is a golden shiny glass-like thing, inside which there is a mosquito. So that is also amber that they showed in that movie. And he extracted the DNA out of that mosquito to recreate dinosaurs. So that's a fiction movie. And amber is used today as well as in ancient times as jewelry. So you can see so many colors of amber. On the left and right, you can see these beautiful necklaces. So this is what people used to wear along with other ornaments in the past. Today we have gold, silver primarily, but amber was used as jewelry, and they would take it to the jewelry person and they would polish it to give it proper shape or give it a shine if it has become dull. And what they noticed, and there is this person called Thales, and he lived in a city called Miletus. He was a Greek philosopher and scientist, if you can call it. And he took his wife's jewelry to a jewelry shop, and he asked him to polish it. And after the person polished it and kept it on the ground, there were grass, straws there, and he saw that they are getting attracted towards amber. And how does that look? So this activity we couldn't do because we couldn't find amber over here. But there is this person who's done this activity, and I'd like to show it. It's a simple static electricity activity. And what he'll do is he'll take a stone of amber and he'll rub it on silk, and it will get charged. So now he's rubbing it on silk. And just like you do it with your ruler, he'll take it to some small pieces of paper. And so ignore the minus and plus for now. And you'll see that the paper get attracted. So this is basically amber that we keep hearing about in our textbooks. So for me, it wasn't very clear because in the book, they wouldn't show pictures when I was a student. So I used to wonder, what is amber? What is amber? So this is actually amber, and it's so today we do it with our plastic straws and plastic ruler. But this simple thing was a source of great curiosity. And this person called Miletus, I'll show you that picture. So this is the one statue of a person's visualization, and his name was Thales. He lived in the city called Miletus. And you can see the dates. He lived almost 2600 years ago, 2600 years ago. And Aristotle respected him a lot, and he called him the founder of natural philosophy. So in the past, they didn't call it physics, chemistry, biology. they term the entire exploration of nature as natural philosophy. Even Newton's book is called Principia Mathematica, and it has natural philosophy. So in those days also, they didn't call it physics. Newton's book was the mathematical principles of the natural world. And Thales is considered very important, not because he gave so many right things, but because of his time. So across the world and in Greece as well, people used to believe that natural things happen because gods do it. So there were gods of thunder, you must have heard. There was Zeus, there was god of war. So there were different types of gods, and gods created natural things. They created the world, they created disease, and everything was so the explanation for everybody, everything was usually given in terms of the act of some god. And this was one person who diverged from all other people, and he gave non-divine and materialistic arguments about nature. So he was the first person who said that we can explain these things without invoking divine explanations, and he gave materialistic arguments. So in that sense, he started the field of science, you can say, at least the Western science, because once you say that we can explain it on materialistic arguments, then you start observing, you start to do experiments, and most importantly, you start to question people and previously held beliefs, because now you know that you can question things. So after seeing the effect of amber, Thales had this explanation that it is attracting things because amber has a soul or life. So Thales said that just like we human beings and many other living things can influence people around us, and we can do it because we have a living force inside us, we are alive. So similarly, this amber is able to attract things because it has some life in it. And this was his explanation. So you can see that it was obviously not correct, but he was giving a materialistic explanation for it. And at that time, amber was the most famous and most explored substance. But there's this very interesting photo on Wikipedia that you get of the effect of static electricity. So you can see that a cat has all styrofoam pieces stuck on it because the cat has been moving and rubbing around and its body has got charged and it is attracting the styrofoam pieces. So now if Thales observed this, he would obviously say that cat has soul or life, but he would also probably say that foam pieces, thermocol has soul or life as well. So if you have a cat, maybe this is an innocent experiment that you can do with your cat. So we'll do a very simple activity to explore static electricity, and I encourage all of you to try it. Let me switch to overhead. Okay. So although you might not have materials, what I would encourage you to do is still try it based on the plastic ruler that you have and the tip of your, so you can use a pencil, a sharpened pencil tip. I'll use a kebab stick. Maybe I'll use a pencil as well. So what you do is you take a piece of paper and you just fold about an inch wide piece of it. And then you can just tear it. And after you tear it, you will get a strip like this. Okay. And then what you do is just fold it in half this way and then fold it.
Can you change the mode? Like we can't do it full screen or on speaker's view, because
Sorry, I didn't understand.
we on the YouTube, it's like you are coming at the corner, so you can change that. You can do it in speaker's view, or you can spotlight yourself.
This way?
You are not spotlighted.
So it's showing spotlight on my screen.
Because
so right now I am seeing myself full screen in spotlight on Zoom. Can you check YouTube again?
yeah, just a second. Yeah, now it's fine. Now it's fine.
Somebody would have to mute. I can hear dogs.
Sorry?
Yeah. So I thought the cat on my screen attracted some dogs. Okay. So you have this strip, right? You folded it, and basically what you do is, I'll try it with a pencil. So now this center point that you get, you can balance it on the tip of your pencil like this. Okay, we'll come back to this. And what I'll do is I'll take a plastic straw, and I have some woolen thread over here. So if you have a woolen sweater, you can try that. You can maybe even try your hair. And if you have a straw, you can use a straw. Otherwise, you can maybe even try it with your plastic ruler. And I will rub this thing. And electricity, especially static electricity experiments, are notorious for not working on screen. So let's see if this works. And if did you see that effect? So now what I'll do, I'll bring the straw near it, and you can see that it's attracting. Right, so this is like a static electricity paper motor, not technically a motor, but this is a very fascinating toy that you can make. So if they had plastic straws, or if somebody would have thought of this toy in the times of Thales 2600 years ago, maybe they would have enjoyed this experiment. So do try this very simple and interesting thing later on. So sometimes we underestimate toys and these very simple and trivial things. But as I said, like, they were experimenting with amber, and they discovered so many things. And we find out ahead that so many of the inventions came about because they were playing around, not especially because they wanted to make an application out of it, but they were just trying to explore nature. Okay. So there is this other experiment that you can do. Now, a lot of experiments that we've already done, because it requires us to have some setup. So we've recorded those things for you. And this is another very beautiful experiment that you can do. So what you do is you take an aluminum empty cold drink can, and you rub a PVC pipe with that same woolen thing. Now the PVC pipe would get charged, and you place the can on a table on a smooth surface. And if you bring it near it, you'll see that the can will start rolling. Right? So this is a very, another very interesting toy. And you can roll it in both directions. Okay. And you can maybe try to replace it with a plastic bottle. So you let us know that does it work with a plastic bottle as well. This is aluminum can is very light, so it works very nicely with it. You'll have to be careful whether if there is too much humidity, you might not be able to charge your PVC pipe properly. But this is a fairly simple and very interesting experiment. And once all this static electricity attraction, and we are seeing so many instances of attraction, just like amber stone, these things are all attracting each other. And at some point, people wanted to create a device which would detect static charge. So if there is static charge somewhere, if you can bring a device near it, some measuring instrument, it will tell you whether it is statically charged or not. So people created something called an electroscope. So I'll show you an electroscope, and you can make an electroscope using very simple materials. So as you can see that this is an electroscope that you can make very simply. So what I have is a glass, and I have put some paper, I have put straw over here, and you need a copper wire. So right now we have an insulated 25 gauge copper wire. People usually suggest that you should take thicker wire, 14 gauge, 16 gauge, but it worked with this. What you have to do is remove insulation from this copper wire and turn it into a spiral. Turn it into a spiral like this. And this is optional, although it helps. What you do is, so this is the open end of the spiral, right? So this is the sharp end of the spiral over here. You put some solder blob. So you put a sphere, a bead, a sphere of solder over here, and also on the other end. So this is the other end of the thing. And you put a sphere of solder over here, like you do soldering in electronic equipments, right? So you just put a sphere over here, and this we are doing to avoid sharp edges, because sharp edges dissipate the charge quickly. And then you need to take some aluminum foil, right? You take aluminum foil. So like any simple aluminum foil you can take, and you cut 2 strips out of it. You can cut 2 strips and poke holes on the top, and the bottom end you have to turn it into a hook. So you just hang the 2 strips on it. And what you can do with this is, I'll show you through that video. So again, if you bring a charged piece near it, you will see that the 2 aluminum foil so this is the front view. This should be more clear. So can you see the 2 foils separating? So we are bringing a charged rod and the 2 foils separate. Now what we'll do is we'll touch. So did you see that? So what he's doing is he's keeping the rod near the spiral and he's touching the spiral with his finger, and observe what happens to the spread apart leaves. So the leaves are spread apart, and notice just as soon as he touches it, the leaves collapse and come together. And now he has taken the rod back and the leaves are again spread apart. Now if he brings the same rod together, they are closing instead of repelling. If he's taking the rod away, and if it, right, if he's taking the rod away, now the leaves are spreading, and if he is bringing the rod nearby, the leaves are collapsing, just the opposite of what was happening earlier. And again he touched the leaves with his fingers, so they collapsed. Let me see if I can show it to you live. So my friend will rub the rod, and let me see if I can show you live as well. Yeah, can you see the leaves spreading? Yeah, now what I'll do is I'll keep it nearby and I'll touch, so you can see the leaves are spread apart. I'll touch this and see what happens to the leaves. Right, they collapsed. And now I'll take my hands away, and if he takes away the rod, they'll spread a bit, so it's leaking a bit of the charge. So this is a very simple thing that you can make, which is called an electroscope. And make sure to remove the insulation where your leaves are hanging. And what is happening in this process is, when we are bringing a charged piece near the spiral, so imagine that after rubbing wool to PVC, the PVC is getting negatively charged, and when we bring it near the spiral, the negative charge repels the free electrons in the copper wire. So copper wire is a conductor, it has free electrons. So it repels those electrons and they move to the furthest point. And there the aluminum foil gets separated, because now it is receiving the excess electrons from the spiral, from the top part. So like charge is repelled and it is free to move. So it moves apart because now there are electrons over here. And if I take the charged object away, the leaves will collapse. Now what is happening when I'm touching it? So now the leaves are spread apart. When I touch it, I am providing a pathway for those electrons to go even further. So in a way, I am earthing the electroscope. So if I touch the spiral of this electroscope, while the PVC rod is over here, the electrons which were going into the leaf can now go even further apart. So those electrons come to my body, this becomes earth, and now there is no excess charge, so the leaves collapsed. And now if I remove the rod, so what would happen? Now the electrons went away from the leaves, so now they have a net positive charge. And that's why when I take away the PVC rod, they were still repelled, even though there was no PVC rod near it. And since they were positively charged, which is the opposite of what the PVC rod had. So this is charging by induction that we see, that the PVC rod was negatively charged, but by this process, the leaves became positively charged. So now if I bring the rod towards it, what will happen? It will repel the electrons again and neutralize the positive charge. So the leaves will come together. And if I take the rod back, the leaves will spread apart again. So this is a very simple and beautiful toy that you should definitely make. And why is this all charging happening? Which object becomes positive, which object becomes negative? Is people have created something called a triboelectric series. And in static electricity, all that we do, this is called a triboelectric effect. Tribo is a Greek word for rubbing. So by rubbing this electricity that is created, it's called triboelectricity, and people have created a list of objects that which one becomes negative, which one becomes positive. Basically, which object likes to give away electrons more, and which objects like to take electrons more. So you remember that photo of the cat with styrofoam pieces sticking to it. So the objects on the top, you can see the plus sign. These objects towards the top like to give away their electrons, and the objects near the bottom like to take electrons and become negative. So the cat's fur likes to give away its electrons very readily, and styrofoam likes to take electrons. So usually when we try to have static electricity effects or this triboelectric effect, we take two substances which are on the opposite side of this series. So you might take something on top. So for example, we were taking wool, which is near the top over here, and we were rubbing it on PVC, which is at the bottom. Or in the case of straw, it is made of polypropylene. So that's also polymer which is near PVC in this series. So we were rubbing wool with straw. So the straw was becoming negative and wool is becoming positive, right? So this is the simple triboelectric series. I would request you to come back to this video again, explore this on your own, and try to rub two different things together. So for example, there is Teflon at the bottom and silk at the top, or nylon at the top. So try to rub nylon and Teflon together. So which one will become positive, which one will become negative, can be an interesting exploration for you. And sometimes we think that static electricity and these models or toys that we make are just for fun, which is true, which is a very important purpose. But after doing this exploration, people made a very fascinating and very important for today's modern world. They made an equipment, and that was called a Leyden jar, and I'll show it to you. So there was this person called Peter van Muskenbroek, and he lived in Netherlands in a city called Leiden. And it was named after that city. The thing that you see in the center, this bottle, it's called a Leyden jar. And he invented it, I think the date is probably wrong over here. He invented it somewhere in 1761, I believe, but 1740 or 1761. And this photo that you're seeing is a design from a textbook in 1898. And on the right, you can obviously see the picture of the person. And so basically what they had is they had a bottle inside which they kept, say, for example, vinegar or salt water. And on the cap of the bottle, they inserted a long metal iron nail. And what they would do is they would bring a charged object near this and touch the top metal rod, and they would keep giving charge to it. So what would happen is the water inside would get charged, and the water and the person's hand by which he is holding the bottle, they are separated by the plastic, or not plastic, but the glass of the bottle that is there. So you have two objects which can store charge. One is the hand of the person, the other is the water inside, which are separated by an insulator, which is a glass. And this was the first capacitor that was made. So the first capacitor is called a Leyden jar. And you can obviously make a very DIY model of it. So this is our version of a Leyden jar that you can make. This is not an ideal bottle that you should be using, because we have left so much space over here without a foil. Ideally, you should use something like this bottle. So something which is very flat on the outside, like a cylinder, so that you can, what you have to do is cover this entire thing with aluminum foil on the outside. So you take aluminum foil and you cut it up to the length of this foil. I'll maybe go to over it. So you just put the aluminum, so you cut the length of the aluminum foil to the length of the bottle, and then you put it on top and make it very smooth. You have to remove the creases and put an electric insulation tape over here and keep removing creases and rolling it and cover it fully and put another tape over here. So this is what we have done with this as well. So you basically use some electrical tape like this. We've used a black electrical tape, and this is what we have done on top. So we have rolled aluminum foil over here. Inside we have put salt water. So you need to put a conducting thing over here. You can even try other liquids as well. So try with vinegar as well. And we have put a wire over here. So we have taken out the plastic insulation from one end of the wire and taped it to the aluminum foil. So this is the outer plate of the capacitor. You put a wire over here, and the other end of this wire, you attach it to a plug, and you have to attach it to the earth pin of your plug. So take a new plug, attach it only to the earthing grounding, that long pin on top. So you have those 3 pins, attached it to the 3rd pin and put it in your socket. So basically what we are doing is we are attaching a wire to the outer foil and grounding it. So you have this plug, you have to open this plug and on the inside attach the wire to this pin, and then you can put it in your wall socket or somewhere. So we are grounding this plate, and then what you do is you drill a hole on top, you drill a hole on the cap and put a screw over here and take a TT ball. Then you take a TT ball and wrap aluminum foil around it and make this very smooth as well, right? And after you make it smooth, it will become something like this. And then you attach that aluminum foil to the screw that you have drilled on the cap. So you have to electrically connect this to the screw, and on the end of the screw, you attach a copper wire like this. Now this you'll have to try which copper wire works best. So first we had tried enameled copper wire like this. It didn't work very well. So what we did was we took a normal electrical wire and removed the plastic insulation. Maybe you don't need to remove it from the entire length. You can just remove the top and bottom part and attach it over here. And after that, you just insert it over here. So you fill the bottle with salt water and the wire will dip inside the water. So now your capacitor is ready. So one plate of the capacitor is this outer foil and one plate is the water inside, which is conductive. And we will transfer charge using this ball over here. And how we do that, I'll show you through a video. So you have to rub the PVC rod. So now you can see that he's inserting the wire and he's closing the cap of the bottle. Now, just like before, you rub the PVC pipe with wool, and as you're rubbing, bring the part that you have rubbed on top of the sphere. So now you can see that he's attaching the, he'll attach one end of the wire to the outer thing and he'll put it in the ground socket of the extension board. So now the outer plate is grounded. And he has also taken a connection from the same wire and he's attaching it to his wrist. Now he will hold the wool in that right hand and rub the PVC pipe. Just a repeat of this. So now you can see that he's attaching the copper wire to the outer plate. And this ball that you're seeing, don't get confused. The same ground wire has different branches. So one branch is this wire that he has taken out, which he's attaching to his wrist. And he will hold the wool with that right arm to which he had attached his wire. So basically, while he is rubbing, the same hand where you have tied the wire, that is the hand that you're using. And as he's rubbing, he's touching the ball covered with foil on top with the PVC wire, so that the negative electron, the negative charge on the PVC pipe get transferred to the ball. Now what will happen is the charge are getting transferred from the ball to the water inside, and the water is becoming negative, and it will repel the electrons of the outer plate, the outer aluminum foil. And where will those electrons go? Through the wire, they will go to the ground. And so we are building charge in this process. And what will happen if I touch one of the plates now? So now if you touch it, you'll see a spark. So this is the spark that we usually see. It's difficult to shoot a video of it, but be very careful with this. Don't charge it too much, because you can get a bigger shock with it. So rub it a few times, 10-20 times maybe, and touch it. Now, how do you discharge a capacitor? If you touch both the plates together with a conductor, so you can discharge this capacitor. So one way to discharge this would be to take a wire, touch one end of the wire over here and the other end to the ball. So you will hear a spark. Or after charging, if you bring your finger over here, you will get a spark over here. What you can also do is take a CFL bulb. After you have charged this, you can take a CFL bulb, and if you put the CFL bulb like this and darken the room, switch off all lights, be in a dark room, you will see a small flash. The bulb will glow for a very short duration. And if you are confused, basically this is the connection from this, and the ball is just connected to the same wire, right? So we just bring this ball. So this ball is connected to this plate. We are just bringing it over here. Don't touch this part. We're just bringing it near here, and that discharges the capacitor. So this is the first capacitor that was ever made after all these interesting discoveries. And capacitor, as you know, is so important for all our modern electronics. Our world runs on these semiconductor devices and capacitors. And I'll show you some pictures of the original setup that they had. So as you saw, this is the person who invented it. And this is a picture from his lab. So what they did was, they had this glass sphere which was tied to a pulley and a belt. So the glass sphere was rotated fast, and a person would touch the glass sphere with his hand. So the rubbing would charge the glass sphere, and there was a metal chain that was connected to the glass sphere. So the charge was transferred from that chain to this bottle of glass. So there was water inside, and a metal wire was dipping in that water, and the person was holding it with his one hand. So one plate of the capacitor is the water inside, the other plate is the hand. And when the person touched the wire with his other hand, he got a very huge shock. And it is said that this assistant of that person got such a big shock that he was in hospital for 2 days. It took him 2 days to recover from that shock. And this inventor, he said, he also got a shock. And he said that even if you make me the king of France, I will not take another shock of this machine, this Leyden jar. So I would not take a second shock for the crown of France. And later on, as you can see, this is the 1914 design. They removed the water from inside. So the design was evolved. Now what they had was, they had a foil, tin foil or metal foil coating on the inside, and they had another coating on the outside. And there was this glass in between, and the inner plate was connected with a metal chain to this sphere over here. So this Leyden jar design was also changed over time. And today, obviously, we know that there are so many different types of capacitors that we have. Now, static electricity was known to ancient Greeks and people across the world from very ancient time. Another thing which was very different from this that people knew from ancient times and which was discovered in China was magnet. So they discovered something called lodestone. And that also, I would like to show you a photo, because we usually hear about lodestone, that it's a naturally occurring rock. There are different colors, different variations in how a lodestone looks, but this is...
Yeah, sorry to interrupt in between. Can you repeat that connection to the 3-pin plug one?
Okay.
Yeah, students are facing some confusion in it. You can repeat it once.
So basically what you have to do is, this is the outer plate of the capacitor. You just take a wire and attach it to the outer plate using tape. Now, where does the other end of the wire go? We don't have an open plug right now, but basically in the market, you get these sort of plugs, right? A white plug, separate plug that you can get out and you can open it from the backside and you see the pin connections, right? So what you do is you take that wire and connect it to this long earthing pin. You have to connect it to this pin. And then if you put it on the wall, this wire would be connected to your home or to your school's earth connection. So this is what we have to do. So basically what would happen is this outer plate of your capacitor would get earth or grounded, right? It's a very simple thing. In our case, we just put the wire in the ground pin. We didn't use a plug, but it's better to use a plug. Okay. So we're talking about lodestone. So this is a picture from a museum in America, and you can see that they put a rock over here and some paper clips, and the paper clips are sticking to it and hanging in air. So lodestone looks like this. There are other types of lodestone that look very black as well. So this is a naturally occurring rock, which is magnetic. So people also knew about magnetism. And as you can see that objects like amber attracting things after rubbing, and that is called static electricity. That was one phenomenon. And magnets attracting and repelling things was another phenomenon. So these two are like electricity and magnetism, two separate things that we know of. And if you would ask Thales what he would say that lodestone also has life. Why did he say amber has life? Because as you can see on this right, lodestone has a soul or life as well. Because amber was attracting and influencing other objects. Similarly, lodestone was also capable of attracting other objects. So these two stones became very famous, and this knowledge was passed down generations after generations that amber and lodestone have soul in them, they have life in them, they are able to influence other objects. And that is where Thales and his contribution becomes important, because after him Aristotle studied it, so many Greeks studied it, that knowledge spread across the world. Now with regards to magnetism, there are many concepts, but I believe most of them are relatively simple enough and are usually covered in your class. What we'll show you is a very simple toy of magnetic levitation, and this is a lady called Hamsa Padmanabhan, and this photo is after she had grown up from her childhood days. But many years ago, she made this toy whose photo you can see on the left. It is called Magnetic Levitating Toy. And we will show you a model of it that also you can try. So I'll go to overhead. So basically what you need is a foam piece, and you need 4 ring magnets, and you need another 2 ring magnets that you can put on a pen or a pencil. And if the ring magnet's diameter is bigger than the diameter of the pen or pencil, you can put some paper to make it snug fit, tightly fit. We've just put some tape over here for decoration. And you need an old piece of CD, right? You can also use an ice cream stick or anything for a support over here. And then you put you put some slits in the foam sheet, and there you insert these two magnets, right? And similarly, at the back also, you make a slit and insert the magnets. This is just a CD piece. And how are these magnets supposed to be arranged? So this magnet over here, if you bring it near these magnets at the back, so the magnet at the back of the pen should be repelled by the magnets at these two magnets at the back. So if I bring it near it, it is repelling. So these two should be in repulsion mode if you touch them on the top. And these two magnets should attract this magnet at the front, right? So you can see that it is getting attracted. And then you put the CD over here. And now if you place the pencil, it will hang in air. And I'll show it to you on front camera. Right? So you can see that this pen is levitating in air. And if I try to spin it, it spins for a very long time because it is spinning in air. So you have to work to adjust the position of these two magnets on the pen. So usually the back magnet is on top of the back two magnets, and the front magnet has to be pulled slightly behind the front two magnets. So this is something that you would have to adjust and try and troubleshoot and see if you can make it spin. And it often helps if you make a small dent or small surface hole on the CD so that the tip of the pencil can get stuck over there. So this is a very fascinating toy that you can use to levitate the pen. And one challenge that we would like to leave you with is, how can you make the same toy with just two magnets on the bottom? Right, so we've made this toy, and you can achieve the same effect using just two magnets over here at the back on the foam. So as you can see, there are two magnets over here and one magnet on the pen, and we have an ice cream stick over here. So you have to find out how do you arrange the magnets in what orientation so that you can achieve the levitation. And the great thing is, this is quite a stable toy, right? And what Hamsa did was, she wrote a paper on this toy and sent it to many science competitions. And you can see that this is the name of her paper, Static Magnetic Levitation Demonstration. She was studying in Kendriya Vidyalaya Ganeshkin High School in Pune. And she wrote this paper, and she also participated in a competition organized by NASA. And after winning the prize, a dwarf planet is named after Hamsa. So there is a planet, I think it's an asteroid. It's named after Hamsa. And in her paper, she analyzed what are the forces acting on it, because for any object to be stable, you need balance of two things. One is that the forces have to be balanced, and secondly, the torque on the object has to be balanced, right? So for example, if I take that same thing, now why this pen is levitating in air? Because while gravity is pulling it downwards, there is a balance of force which is pushing it upwards, which is cancelling gravity. So that is why the force in the vertical direction is balanced. Similarly, force in the horizontal direction has to be balanced. So in this, there is a force that is being exerted on the CD, and CD in return is applying a force backwards on the pen. There is another force in the vertical direction, which is that of friction at the tip. So In the vertical direction, there is the force of magnet, there is the force of friction, and there is the force of gravity. And in the horizontal direction, the force exerted by the pen, which is being pushed by the magnets, and the reaction force by the friction. And at the same time, like we discussed in our laws of motion episode, so if net force is 0, that doesn't mean the body will be at rest in all respects. If the forces do not cancel out in axis, the body will rotate around its center of mass, right? That's what we saw with that demo where we were pushing a person on the floor. So for this object to be stationary, the forces have to balance as well as the torque has to balance so that it doesn't rotate. So the beauty of this toy is that the various forces work in such a way that the torques and the forces all balance out. And in her paper, she has shown these forces that at the back, the magnets are repelling it upwards. So this pink arrow upward shows the magnetic repulsion. The front magnets are attracting the front magnet. So it will be at an angle. So you can decompose it into two directions. One is the vertically downwards force shown by the red arrow. One is the horizontal force to the left shown by the blue arrow. And on the CD, since the pen is pushing the CD will push the pen towards the right, shown by the N letter normal force. And there is a friction force in the vertical direction shown by this orange arrow, mu times F. So this is the balance of force. And I encourage you to go through this paper that she had written. So this is a fascinating toy that you should all definitely make. Magnetism is a very fascinating topic. And just like people were exploring static electricity, they were exploring magnetism. And one person is very famous and respected for his discoveries in magnetism, and he's called William Gilbert. He was a person who lived in England in 16th and 17th century. And after doing a lot of research on magnets and after reading about the work of Greeks, static electricity, he wrote this book in Latin, whose title in English is On the Lodestone and Magnetic Bodies and on the Great Magnet, the Earth. And this book was published in 1600. You can see the cover page on the right side. And it was William Gilbert who gave the name electrics or electricity, because amber is called electron in Greek language. So he called all objects which on rubbing become charged. So those objects he called electrics based on this word electron. And it was William Gilbert who for the first time proposed that magnets point towards north because Earth is a huge magnet. So he was the person who first proposed that the Earth is a magnet. He proposed many other things, but with regards to electricity and magnetism, these are some important points that he said. How static electricity is different from magnetism? He said that electrics, the material which becomes statically charged, electrics can only attract, while magnets can attract as well as repel. Now I have put this in red because I want you to think whether static electricity can only attract or it can repel as well. The second point is said that electric need to be rubbed to get charged, but magnets are permanent, right? So like lodestone, you don't have to rub it to make it charge and behave magnetically. Third thing he said was electrics don't work underwater or on humid days. So if you have lots of humidity, static electricity doesn't work very well. But water does not affect magnet. Magnets will work even underwater. And he said electrics can attract any type of material, but magnets can attract only some metals. Attract as well as repel, magnets. So these were four important points. He said how magnetism is different from electricity. And coming back to this first point that electrics can only attract, this was a wrong thing that he was saying. So he did a lot of research, but he did not do experiments where he would see the repulsive nature of electric charge and electric force as well. And there is a very fascinating activity using Tinsel that you can do. And I'll show you that activity in a video, and that utilizes the repulsive force of electricity. So what you need is a thermocol piece. First, let me show you the setup. What you need is like this thermocol sheet. We have taken the type of thermocol that is used in your craft work. we tried a few other thermocol pieces as well. Surprisingly, and we don't understand it, not all type of thermocol is working. So you will have to experiment a bit which type of thermocol works. Then you take your normal, you can take any woolen cloth as well. We have thread, so we used a thread, and this would be used to rub it. And you remember that triboelectric series that we mentioned. So if I rub wool on thermocol, the wool becomes positively charged and thermocol becomes negatively charged. Then you need an aluminum pan, right? So you must have seen these type of pan, like they sell chart in it and they pack it. So these are disposable cans. So you need one type of can, and you open this up and make it flat. So you make it flat like this. And at the back, you cut another piece of thermocol and tape it or glue it to the backside. So this becomes your handle. So this is how we will use it. And the final thing that you need is tinsel. So you must have seen these things which are used in decorations. I think this one is from some cheerleader to wave it around. So you need these type of things, and they supposedly have a coating of aluminum on top of it, a very thin coating, and these are very light. So we'll just take one thread out of it, and you have to, so what you have to do is you have to take one tinsel thread and tie a knot and make a ring out of it, right? So you have to make a ring of tinsel. And what you have to do is, I'll show you the video. So first, rub wool and thermocol. So you rub it properly, and you have to do it when there is less humidity. Then you place the aluminum foil on top, and after placing this aluminum plate on top, you have to touch it with your finger. So just notice that he touches it with his finger. And after touching it, you have to lift it with the handle, the foam handle, and you place the ring of tinsel on it. So you can see it flies in air. There is levitation, electric levitation. You just drop that tinsel on the plate and it will fly in air. And this is due to electrostatic repulsion. And if you put your hand, it bounces. This is so fascinating that it will bounce up and down. It will touch your hand, then it will go down. It will bounce up and down. And then you can charge it again and again if the charge disappears. So you put the plate again, touch it with your finger, and it will get charged again. And now again, if you put a CFL lamp on it and turn off the lights, you'll see a flash. Did you see that flash? So let me show you again. So you can see that there was a flash in the CFL bulb, right? So this device was something which was invented in 1762 by this person called Johann Carl Wilck. And it is called the Electrophorus. And as you can see that there is a plate with an insulated handle and there is another plate at the bottom. And at that time, they used different materials for the bottom plate. They used wax, they used resin. In our case, we use thermocol. And on top, this circular top plate was of metal, which in our case was that aluminum pan, and you had an insulated handle. And what they would do is, you can see that there is a cat fur over here, a dead cat, and they would charge the bottom plate and then touch the upper plate. And what is happening, as you can see on the left, the bottom plate after getting rubbed with fur becomes negatively charged. And when you bring the top plate near it, in our case, when we are bringing that aluminum plate near it, what will happen? The negative charge on the thermocol will repel the electrons in the metal aluminum plate. And there would be positive charge on the bottom, negative charge on the top. And when I touch the top surface with my hand, what will happen? These electrons on the top will go into my body. And when I remove the plate will become positively charged. So we can see it using this animation. The thermocol is negatively charged I bring the aluminum plate, bottom becomes positive, top becomes negative. If I touch it with my finger, the electrons go into my body. And now the aluminum plate has a net positive charge if I remove it now, right? So now the aluminum plate is positively charged. So that is why I'm touching it. And after I touch it, this becomes charged. And what is happening with tinsel? So when I drop a ring of tinsel on it, so when I drop it, right now it is not charged, so it won't levitate. But when I drop it on this aluminum plate was positively charged and this is neutral. So as it falls on it, the plate attracts some electrons and this becomes positively charged as well. And now the plate is also positive because after attracting a few electrons, the charge doesn't disappear. So now this is positive and this is also positive. So both repel. And since it is so light, it floats in air. So this is a very fascinating activity of electrostatic levitation. And you should definitely try this, and you even try that CFL activity. You can even bring an LED near it. So if you have an LED, if you bring it near it, and if you are in a dark room, you would be able to see that the LED also glows. So this is an LED. So if you touch the pin to the aluminum plate, that also glows. And a friend of mine has written these 3 comic books in English as well as Hindi. So if you can send us an email, we'll give it to you. And these are very beautiful comic books he has written called Michael Binds the History of Electricity. And in Hindi, it's called Michael Ne Buna Vidyut Ka Ityas. My friend Sachin Dutt had written this. And these are 3 comic books, 3 volumes. And he talks about right from Thales, from Greeks to Michael Faraday, how electricity, discoveries of electricity, static electricity, magnetism, and all were made. And coming to the next stage in our discovery of electricity, we would like to thank a frog, because of which all of this was possible. And there was a person in Italy by the name of Luigi Galvani. And I'll show you his picture. So this person is called Luigi Galvani. And in 1781, he made an accidental discovery. And what he discovered is something that we should see. So we don't want to kill any frogs. And I think even live dissections are not done. But a university in Paris has done this experiment, replicated what Galvani did in 1781 and made a video. So we usually hear that a frog leg moves, just like we have heard of amber but never seen it. At least we've now seen it in photo. Similarly, what he discovered, let's see. So they dissect the leg and they take out a nerve in the leg. So they'll put a glass stick and bring out that nerve slightly. So then now they put some glass stick over here. And this is a device which generates static electricity. So what Galvani discovered was he had a lot of static electricity equipments. And when he touched the leg of the frog with static electricity, it moved. So this is a dead frog. So you can see that the leg is twitching. This is dead. This is not alive. Just by passing electricity. And now what he did was he placed a zinc sheet at the bottom and he took a copper wire and he touched the zinc sheet with the copper wire and touched the other end of the copper wire to the nerve of the frog. So you can see that the frog is behaving as if it is alive. Right? So this is what this person did, a lot of experiment on frog. And he said that I have awakened this frog and I have discovered animal electricity. So it's written over here that a frog preparation contracts when somebody, so there was his assistant or his wife who were helping them. So when they put the static electricity machine in contact with the frog's leg, or even near the leg of the frog, the leg of the frog moved. And some people today have recreated this version using cockroaches. So this was a very fascinating video I found, that they've done the experiment using cockroaches. Again, I would not really recommend you to kill the cockroach. In this experiment, what they did was they have their own cockroaches they keep by themselves, and they take out one leg of the cockroach. And the good thing about the cockroach is that that particular leg grows back again. So they take out that leg, and the cockroach in 6 months will have that leg again. So we'll see this video. He takes out a cockroach and immediately puts it in ice water so that the cockroach goes in sort of a coma. It goes into hibernation if you put it in very cold water. So it won't feel any pain. Now he will remove the leg of the cockroach. So this is a live cockroach. So he pulls out a leg of the cockroach. And he's showing that the leg will grow back again. So after 43 days, you can see that the leg has grown out. This leg was broken. And after 125 days, about 4 months, this entire leg has grown back again. So the cockroach wasn't really harmed in this process. And now what he will do is, he has created a small battery that we will see. He will put 2 pins in the leg of the cockroach. And he will attach one terminal to one pin. And if he brings the other pin of the battery, you can see the leg is moving. Right, so this is my Backyard Brain channel. They do experiments on neuroscience. So this was so fascinating that Galvani had discovered, and everybody was so excited and so confused. And you must have heard of that novel called Frankenstein. So there was this lady, I believe the author of the book was Shelley. So she became concerned that people are doing such kind of experiments with organisms, with animals. And I haven't shown you some videos, but is somebody talking to me?
Yeah, I have muted those.
Okay. Yeah, so she became concerned that using the power of science, people will create monsters, and therefore she wrote that book, Frankenstein. Maybe you can read that book. There are even movies made where they create a live human being. So it's a science fiction novel. They create a live human being and they breathe life into that dead human being using electricity. So it was based on these experiments. And Galvani then wrote about his findings. Right. So in 1791, after his researches, he published his findings, and on the left, you can see the paper that he had written. And this is an image of his lab. There's not a photo, but somebody has drawn a photo that he was using so many frog legs. He had this electricity machine. You can even see over here the Leiden jar. Notice carefully, you have a Leiden jar capacitor over here. So using capacitors, people were able to do many experiments. And so we won't go into much detail, but basically after connecting those two things, he got some electricity, and he felt that this is something which is inside the body of the animal. But after reading his experiments, this person called Alessandro Volta, he disagreed with Galvani. And in 1794, after his research, he published his findings, and he said that Galvani is wrong. There is no electricity inside frog. Frog legs are only acting as conductors for current. And you can replace the frog legs by any moist conductor. And electricity is flowing because the two metals are in contact via the frog's body. And he took combination of different metals, and he put those metals in his tongue, and he used his own saliva. So he would get like a shock, and there he would test that electricity is flowing or not. So this is the journal Philosophical Transactions of Royal Society and his paper where in 1800 he wrote about his findings. And he is very important because he developed the first battery that was ever made. So one battery that was made was the Leiden jar that we saw, but it was statically charged. It would dissipate in one instant. So it was a battery which was storing charge, Leiden jar, but as you see that the charge discharges in a single instant, we do not get a continuous flow of charge. But in 1800, Volta made this Voltaic pile using rings of sheets of zinc and copper. Sometimes he would use zinc and silver. And on the left, you can see his setup. And on the right, you can see that basically he put zinc, a layer of paper soaked in some acid or salt water, and then he put silver or copper, and he created a stack of this. And this was the world's first battery that was made in 1800. And the interesting thing is we can make a model of this first battery as well. And what you need, I'll show it to you on overhead. And this is something you must definitely try. You take these old 5 rupee coins that you get. So now you get those very steel type 5 rupee coins. But if you get these coins, you take a lot of, at least 4 coins you should take. And you take aluminum foil and you cut rings of aluminum foil as well. Right? You can make rings of aluminum foil and you have these 5 rupee coins. And these 5 rupee coins are made of nickel and brass alloy. And then what you have to do is you take a cardboard and you soak it in vinegar, right? So you have any vinegar, you can use salt water as well. You can use a mild acid as well if you can do it carefully with your teachers. You can use lemon juice. You can try different. So you try different juices of vegetables and fruits as well, right? And you take this cardboard and you dip it in vinegar. So basically, you take pieces of cardboard, you cut circles, and you dip it in vinegar and leave it there. After some time, the top thin layer will peel away, right? So you can get these thin things. So what you can also do is just cut pieces and soak it in vinegar. After some time, the top thin layer will peel away, and then you can cut circles out of it. And then you take some tissue paper and put these soaked pieces of cardboard on it so that the excess vinegar and all, it is getting absorbed. You don't want it to be dripping. It doesn't have to drip. You can absorb the excess. And then what you have to do is take one coin, right? I'll take this. Take one coin, put that soaked cardboard on top, and then take an aluminum foil and put it on top. So you are basically creating an electric sandwich, right? So what I have is a coin, cardboard, aluminum foil. Then I will take another piece of soaked cardboard. Sorry. Then I'll take another coin. So coin, cardboard, aluminum foil, coin, cardboard, aluminum foil. So I have 2 now. So again, I can place coin, cardboard, aluminum foil, and I'll place a 4th one as well. So I have coin, cardboard, and aluminum foil. So we basically get this type of sandwich, just like Alessandro Volta made. And I already have a ready-made one, but I'll try to see if this one also works. So we'll switch off the light. And I have an LED over here, right? And let's see if this works. Are you able to see this is working? A very bright light. Now I have, so this is something for you to explore. An LED has a positive and a negative leg. Which one should I connect to aluminum and which one should I connect to the 5 rupee coin? So you can see it's a very bright light that you're getting. So you can create a handheld battery, replicate what, so you can imagine the excitement of Alessandro Volta. Obviously he didn't light a bulb, he didn't have LED at that time. So this is, we can use another LED as well. So I have a red LED. So you can see I can light up a red LED. And a very interesting thing is I have this red LED. And if I bring back my green LED, so you can see that as soon as the green LED is lighting up, the red one is turning off. And this is something interesting to explore, that it's almost turning off, the red one. I'm not removing the connections of red one, but it is turning off on its own. And we also have some copper strips and some zinc strips. So just like Alessandro Volta, you can use these also to create a, so you can use these also to create that Voltaic pile or sandwich. So we have cut small pieces of it and created a stack just like we did for coins. And let's see if this is working. So I think this has dried up. So we had prepared it before the session. That seems to have dried up a bit. You can also use, so we had also brought some copper. We had also brought some copper coins, and we have some galvanized washers. So this is zinc and this is copper. So we had similarly, so we had these many copper coins and zinc washers. So if you get copper sheet, you can try that as well. And we had created a stack of it. And let's see if this works. Right, so this is also lighting up. You can also see a red light. So such fascinating things people discovered, and Volta's big contribution to our world was this battery that he made called the Voltaic pile. And I would definitely encourage you to try this. If you get copper, zinc, you can try it with that. But definitely this 5 rupee coin battery that we just showed you, you should make it. And this is how Galvani proved that you don't need actually a frog to generate electricity. The electricity was coming because of the two metals and the electrolyte that was in between, right? And just like we had the Triboelectric series, we also have this something called Electrochemical series. And this is a series where elements are arranged in a particular order. So right here, you can see lithium, magnesium, aluminum, zinc, iron, nickel, hydrogen, copper, silver, gold. And from top to bottom, there is a decreasing tendency to release electrons, which means that lithium has the highest tendency to give up its electrons and gold has that least tendency. Hydrogen is in the middle, and that is the reference point we take for 0. So in our Voltaic pile, or in Volta's Voltaic pile using zinc and copper, what was happening? Zinc was losing 2 electrons to become zinc ion, and those 2 electrons were traveling in the wire and going to the copper side. And at the copper side, what is happening? Oxygen from the atmosphere is getting deposited, absorbed on the surface of copper. at the cathode, it is combining with water in the electrolyte, in our case, vinegar or any acid that you take, and getting 4 electrons that came from the zinc side to make hydroxide ions. And this is how the EMF is getting generated. There is this very interesting article that I would recommend you to read in the Journal of Chemical Education called The Role of Oxygen in the Voltaic Pile. Because till now, people used to think that at the cathode, hydrogen is getting emitted, and that is the primary mechanism. But what they did was, they placed this Voltaic pile in a jar which was filled with carbon dioxide from a burning candle. You can also use dry ice. They also put nitrogen in it. Basically, apart from oxygen, they put different gases. And then they saw that if you replaced oxygen, the voltage of this Voltaic pile decreases a lot. It doesn't work as much, which means that it is not hydrogen formation, which is the major mechanism at the cathode. It is this formation of hydroxide ions, the reaction of oxygen that you're seeing here at the cathode. So this is a very interesting new paper that was published only very recently in 2021, the role of oxygen in the Voltaic pile. Right. So, Sonal, let me know where we are and how much where we should conclude all of this. Because there is, as I said, there are so many other things that are to be done, and we haven't yet reached Faraday. There are so many other activities, but these that we've seen till now, you should definitely try. Sonal, if you let me know if we should stop here or maybe take 5-7 minutes more, then accordingly I'll go. As per the
We
consent.
can take 5 minutes more. Then we'll wind up the session. It's 4:35. We'll extend it till 4:40, and then we'll wind up.
Okay, so I'll quickly go through other things, and maybe later on, you definitely watch our 3030 Eklavya episode, which would be coming out soon, and there we'll try to accommodate all of this. And after this, people really started to think, so from electricity, we can generate heat. We also know that electricity generates light. And till now, electricity and magnetism were two separate things, and people were really wondering, are electricity and magnetism also related? And then people were thinking, and you can imagine the importance of Volta's battery, because till now you did not have a source of continuous reliable current. And after he made the first battery, Humphrey Davy used it to discover new elements, and people used it for so many purposes. So his battery was really a milestone in science, because now they could do electricity experiments properly, and they didn't have to rely only on static electricity and Leyden jar. So people said that if there is a current in a wire, what will be the direction of magnetic field in that wire? Will it be parallel to the wire along the direction of the wire, or will it come out radially from the wire? And this person, Oersted, in 1820 discovered that when you pass current through a wire, and if you put a compass needle, it deflects. And this was the first proof or first discovery which combined electricity and magnetism, because now we had evidence that electricity produces magnetic field, because a compass needle is deflected only by magnet. And if a current carrying wire was deflecting it, that means it is generating magnetic field. And you can do this experiment yourself as well. You take a wire and align it in north-south direction. So this is north, this wire is put in north-south direction, and you hang two ring magnets with a thread. You can also use a compass needle, and you can see two alligator clips, and we have attached it to about 6 or 8 volts. And if I now turn on the supply, you can see that the magnet is deflecting. If I turn it off, it is back. If I turn it on again, it is again deflecting. And if I put the magnet below the wire, the direction will change. Now I'll switch on the current. It will spin in the other direction. So this is an experiment that you can do. And he discovered that if there is a straight wire, the magnetic field is circular around it. And this was something really fascinating and new, because until now there was, because if you look at gravity pulls everything towards it, towards the center of mass of the two bodies along that straight line, right? Electric charge is also, electric force is along a straight line, but magnetic force is also along that straight line. But a current carrying wire was producing a circular magnetic field. and you have that right hand rule that you use to find out the direction. And you can also do this using this very simple activity. We took this 25 gauge wire and made a rectangular coil with about 40-50 turns. And now we are sprinkling iron filings on it, on this paper. So this is an insulated copper wire, 50 turns. We are sprinkling. You can use a channi, a sieve that you use for tea, to sprinkle these iron filing powder, and connect the two ends of the coil to a DC power supply. I think we used about 8 volts for this. Now, after I turn on the current, you'll see, and if I tap the paper, you can see circular patterns. So the straight wire is going inside the paper and it is generating a circular magnetic field. So this is what this person Ørsted discovered, that a wire produces magnetic field and that magnetic field is circular, right? And then there were many other interesting things. People started saying that the current does not flow in a straight direction. The current must be flowing in a spiral. That is why it is creating a circular magnetic field. And that is where Faraday comes with his beautiful experiments. And he makes a motor, the world's first motor that he makes, which proves that the current flows in a straight direction, but it provides a circular magnetic field. In 1821, he did this, and this is his paper, which was published in 1822, and a photo of the setup that he used. We will do a very simple version of it, and which is basically, you can do this by yourself. And I think this has audio, but I will. Yeah. So basically we have salt water, we have a cycle spoke from which a wire is hanging, paper clip, and we have a 9-volt battery. And on this side, we have an aluminum foil which is dipping inside that water, salty water. So negative terminal is attached to this cycle spoke from which wire is hanging. And there are magnets inside this container of salt water. And when I switch on the current, this wire will start turning. And this was the world's first electric motor made by Michael Faraday. Now, when I switch on the current, you can see that the wire is rotating. And we'll show you the top view, and you can see the magnets inside. Now, the difference was Michael Faraday used mercury. He did not use salt water. He used mercury. Till then, they did not know the harmful effects of mercury. And this is the world's first electric motor that he made. Right? So this is where we'll end. There are so many fascinating things about this. And the important thing is this was a useless motor. This was a useless motor because you cannot do much work using this motor. But he did not make that particular instrument to run a fan or for some application. He did just to explore what direction does current flow and does it produce a circular force on metal. In fact, there are many other things that you can make. This is a DC motor that we make and show. Maybe in Eklavya episodes or in some workshops, we'll try to show it again. A very simple DC motor that you can make, right? It just requires a cell, magnet, safety clips, and a coil. So if you want more of these things, I would suggest that please come back to this video again, do all those activities. If you have confusions, questions, write to us. We'll try to help you. Of course, as I said, learning concepts and understanding them is one object, but more importantly, the effort to make a model work, the frustration that you will have when it will not work, the things you will think, why is it not working? You will try to link it to theory. So those are very important learnings, and I would really encourage you to try all these things. Send us your videos and feedback and your questions as well. I hope you got a glimpse of a sort of historical journey of electricity and the great work, so much effort, so much patience these people put in, because of which we have a modern understanding of electricity. It's a huge topic. But thank you so much for enduring me. Sorry for taking so much time, and over to you, Sumit.
Yeah. Thank you, Ashutosh. It was such a power-packed, session, and it was a great session. Like, इतने short duration में we learned so many experiments, इतने सारे interesting चीजें देखी, and it was something like it was very excellent. So we have also got a feedback. Thank you, sir. It was excellent session. Yeah.
And I would really like to thank my colleagues, Vinod, Dinesh, Sajid, Rakesh, Shrisha, and it's like this entire team of 20 people who works every day to make these things, because of which I can sit here and present these things.
So thank you, students, for joining. Thank you, teachers. Thank you, everyone. And as Ashutosh said, that you can come back to us like anytime. You can go through the videos, and in case you have any doubt, you can write back to us, because these are such important experiments that it will help you in future also. And you may be like not understanding it in one time, but you can always come back and see these videos while revision, and you can ask the if you have any doubt, and do try doing these experiments at home. Do try keep doing practice, keep practicing these experiments and everything, and then you will learn more, you will learn better. So thank you, Ashutosh. Thank you for the wonderful session. Like, I enjoyed a lot, and I know students would also have enjoyed it a lot, because इतने सारे experiments इतने short duration में समझना, it's very difficult, but it was very nice. Thank you so much. Thank you, students. Thank you, teachers, for joining. And yes, for the assignment thing, you can always go back to any of the assignments and you can attempt those. So the assignments links are open for all the assignment. Please attempt the assignments. It is for you. So do the assignments. Yeah. So Ashutosh, we can end the session now. Thank you, everyone.